Okay, so today is day 7 of our Fixman theory summer school. My name is Joe Baker from College of New Jersey, and I'm going to be talking to you today a little bit about protein simulation, how to set up protein simulation, some of the things to be careful about as you're preparing, protein files that you either generate or download from the protein data bank. And then building upon what Elijah talked about yesterday in terms of the different phases of a simulation, how to kind of appropriately get through minimization and equilibration and production phases to get to the point where you can acquire data that you want to analyze. And then tomorrow, what we're going to do is we're going to go through kind of several analysis kind of packages. We'll use a bit of visual molecular dynamics tomorrow to do some analysis and visualization. We'll use VMD a little bit today. We'll use another tool that comes along with Amber Tools, which is the kind of companion package to the Amber simulation software. So there's an analysis tool within Amber Tools called CPP Trash, which is quite useful for a lot of analysis. And then we'll also spend a lot of time with MD analysis, again, using MD analysis to script up various simulation analysis routines. So let's go ahead and get started. So first thing I want you to do, go ahead and log into your accounts on the cluster. And in the workshop shared directory, if you go into my subdirectory, so the Joe Baker subdirectory, you should see a day 7 zip file. So go ahead and copy that into your directory. If you already copied it from before, copy it again because I updated some of the files today. So go ahead and grab that file once again. And then once you have that file in your own directory, if you just type tar minus xvf and then the name of the file and hit enter, it will extract all of the files into a folder called day 7. I'm not actually going to hit enter and do this because I already have the folder there. But so copy that first and then extract that. And then in just a minute, we'll go ahead and take a look at what's inside of the day 7 folder. Okay, has everybody been able to get that and extract the folder? Anybody not have the day 7 folder yet? Going slow. Okay, we'll wait just a second then.
You have to put the CP type in R just to make sure that everything comes out.
It's just a file that you're copying, so you don't need a recursive copy. Recursive copies are for directories.
And we're opening like this TQZ file. It's just going onto our local computer. All these.
No, this is on the cluster.
Okay.
So you're logged into the cluster. So when you run that command, it happens on the cluster. That folder is in your directory tree on the cluster. Did it work?
Yeah, just a bunch of lines.
Yep. Yep, that's from the -v option. That's verbose. So it's showing you everything that it's doing as it's doing it, what all the files are that you're actually extracting. Well, it will still be going. So I mean, if you cancel it, you're just going to have to start over. So just let it run to the end. You can cancel it with Control-C. Usually, will let you exit. But yeah, we need to extract them all. So just let it run. Probably everybody doing it at once. That's Has anybody's finished yet? I mean, they're small. They're like, 50 steps or 100 steps or something like that. I mean, it should be quick. It's like, I think 70 megabytes total or something. Okay, so anybody finished yet? Okay, in the meantime then, let's go ahead and jump ahead a tiny bit. While you're doing that, let's go ahead and look at the protein data bank, so which is one of the first things we do. I'll show you a little preview of what's in the folder. So basically what you're going to be doing today. So there's the Amber 15 manual, which Elijah also showed to you yesterday. This is a handy tool to have. One of the things I'm going to ask you to do is today, as you go through and you run your own simulation for your project at the end of the day, is to use the manual to figure out what each of the flags in each of the input files means and comment those lines. So that way, it's not just a flag or a parameter in the input file that you have no idea what it is, but you can add comments to those lines. So you're going to go through that. That's why I added the Amber manual to this. We have a couple folders, which are proteins we're going to take a look at. The first one is kind of a classic fast folding protein. It's used to benchmark typically a lot of MD methods. It's kind of one of the first tutorials you see for a lot of the various simulation packages. It's called trip cage. It's 20 amino acids long, so it's very tiny. So what we're going to start with today, what we're going to go through during the couple hours we have together, is we are going to create parameter and coordinate files using TLEAP for the trip cage system. And then we're going to run the various phases of simulation and kind of go through what a protein protocol for simulation might look like. Of course, we're doing everything with much shorter time step in general, number of time steps in general, than you would do in a true production simulation. And so, when you go into your research projects, you'll want to think carefully about the exact protocol you want to use based on protocols that have been used of other similar systems to what you're trying to simulate. You can find stuff like that, of course, in the literature. But today we're going to do kind of a streamlined process so we can get it done within the time that we have. The other protein that we're going to look at is a slightly larger protein called FAEG. It's a bacterial adhesin. We're not going to do too much with this one, except point out that sometimes when you get structures of proteins, you are missing various regions of the protein and they have to be modeled back in. There are a variety of tools that can be used to do this. The one that I'll talk about briefly today is called Modeler. It's a set of Python scripts that can be used to model back in. For example, one of the things can be used for is model back in missing loop regions in proteins, so short sequences of amino acids. It can be used for much more sophisticated modeling as well. We're not going to go into any of that, but I'll show you kind of how to set up some of the input files for Modeler. We don't have it installed on the cluster, but it's a fairly straightforward Python install that you could do, for example, just in your home directories and get that to work. So after that, you'll have, and I went back one directory too far, but you'll have your project for today, and the project for today is going to build upon what we talked about this morning, which is mostly setting up this trip cage system. And so in this folder, there are going to be just some notes about what the various protein files that you're going to be using are to set up another simulation. So I've chosen 3 proteins from the protein data bank that are relatively small, so they should run fairly quickly on the cluster. And what you're going to do is I'm going to pair you up into groups of 2, and you're going to run some simulations in slightly different states of the protein and compare those simulations with one another after you finish running them. Okay, so in the trip cage folder, I realize that you may not have that all set up yet, but in the initial structure subfolder, there's a file called 1L2Y.pdb. Okay, so does everybody have the folder fully decompressed now or unzipped now? Okay, so if you take a look at the contents of this file with VI, for example, it has a lot of information in it. This is a file that has been downloaded directly from the protein databank. It is a PDB file, and we're going to go through some of kind of the main features in the PDB file that you might be on the lookout for as you're setting up a protein simulation. So let's go ahead and see where the file came from in the first place. So if you open up a web browser and you just do a Google search for the protein databank, this should give you a link that's clickable to the rcsb.org website. And this is a protein databank. It's a repository of crystal structures, so from X-ray crystallography, NMR structures. There used to be theoretical structures deposited in the PDB as well. Those are no longer actively deposited in the PDB, but I think they still have a theoretical model repository somewhere. I'm not absolutely sure on that. But basically what this is a catalog of experimental structures of proteins that, you know, at its core, what it gives you are those initial structures that we need to run a simulation. It tells you where the coordinates are. You know, you've been talking about benzene, these very small systems so far, how to generate coordinates for small molecules. Well, you can do that using these simple kind of geometric arguments that you made in some of the other days, of course. But for a protein, you know, these are much more complicated molecules, right? So we tend to want to get those structures from experiment if we can. There are other ways to do this as well. We can build models, what are called homology models, of proteins of unknown structure based on their similarity of their amino acid sequence to other proteins. So there are ways to generate theoretical models of proteins. But the stuff that we can download from the PDB are experimental coordinates. And so if we take that 1L2Y accession code, which is the name of the PDB file in that initial structure directory, and we type that in here, so L2Y, and hit enter, it will take us to the page where that structure is deposited. And so the first thing you'll see on the protein databank website is, you know, some type of image of the protein, give you some idea of what it looks like structurally. You'll have a bunch of tabs you can click on. You start in the summary tab, and you can get a bunch of information about what you know, resolution the crystal structure was acquired at, other experimental details from the protein databank. You can look up, for example, the by clicking on the Seek tab, you can find information about the primary sequence of the protein. So this is the primary amino acid sequence of the protein, for example, listed here with a map of its secondary structure over the top of that sequence. So how many of you have taken biochemistry? Has anybody not taken biochemistry yet? Okay, so proteins are made of amino acids. The primary sequence is the string of amino acids that defines a particular protein. The next level of structure that we talk about in a protein is what is called the secondary structure. So those would be, for example, if we look back at our image of protein here, this is like a helical structure. We also have other structures, for example, beta sheet structures. We'll take a look at different types of proteins. When we look at the FAG protein, you'll see these beta sheet structures in there. So you talk about secondary structure. The next level of structure is tertiary structure, which is kind of the three-dimensional fold of the protein, how it you know, forms into some type of three-dimensional structure. And then you can have even higher level structures. For example, if you have protein complexes, so you know, maybe your protein doesn't act as a monomer, but it acts as some type of dimer or hexamer, and so this would be like a higher level structure built into the protein system. So basically, the PDB page for a protein, it's useful. You can find the paper that the original structure came from, and clickable links to the article typically. So one of the things you're always going to do when you're setting up a simulation is understand the system you're simulating. So the PDB webpage for that protein has direct links to the primary source. Sometimes if you're really working on like a new structure, the paper's not deposited yet. Structures often get deposited a little bit ahead of the paper. You want to be a little cautious of that sometimes. Make sure that you're able to get as much information about the system that you're simulating as you can. And then there should be a link on here that allows us to actually download, the download files and display files links. So you can display, for example, you can look at the PDB. So this is the same file that we have over here in our terminal that we downloaded. This is the PDB file. And you can view it. And then you can also go to download files and download it. And so that's what I've done and then placed inside of your initial structure file. So this is one of the first places that you might go when you're trying to set up a simulation of a new protein system. Okay, so let's take a look inside the PDB file a little bit. So in your VI window, go ahead and type / and then type the word atom and hit enter. And this will take us down to the section where the coordinates of the system are. So, most importantly, the PDB file contains the atomic coordinates of the system you want to simulate. So these are your initial positions for the system. It has, the atom name, and so this is nitrogen, alpha carbon, so on and so forth. It has the amino acid 3-letter code. And so one thing that, especially if you haven't taken biochemistry yet, and even if you have, download one of these nice graphics that have the amino acid names, their structures, their 3-letter codes, and their single-letter codes, because you'll see all different ways of talking about these in the literature, and so you should get familiar. This will eventually become second nature. Be able to read these and understand which amino acid folks are talking about when you see something in a paper or something in a structure, and then have a sense of, is that amino acid one of your positively charged side chains, negatively charged side chains? Is it a hydrophobic amino acid? Is it polar? So on and so forth. So this is a useful, I would say something to tape on your wall and stare at every day as you work on modeling and simulating protein systems. Okay, so let's go back to the PDB file itself. So it has these amino acid identifiers. This column here, this numerical column, is the residue number. So this is the first amino acid in the protein, and then if you scroll down a little bit, you'll see that flips to a 2 when the amino acid has changed to a leucine, and so on and so forth. If you scroll down, you'll see that there's a whole sequence of residues in the trip cage system. The next 3 columns are the coordinates. So these are your X, Y, and Z coordinates in the protein databank file. These are what are going to define the initial positions of the system for your protein, for your simulation. Okay, so if we scroll down a little bit in this one, this trip cage file actually comes from an NMR structure. Typically, when a set of NMR structures are deposited in the protein databank, they deposit more than one snapshot, so they deposit kind of an NMR ensemble. And so if we scroll down a little bit, eventually you'll see amino acid 20. I told you trip cage is 20 amino acids long. Then you'll see this TER line. So this is the end of that first snapshot of trip cage. End model 2. And so then we go through the same 20 amino acids again, but what you'll notice is that these coordinates, so for example, this first nitrogen for the first amino acid has an X coordinate of -6.919. If we go back up, you'll see that there the x-coordinate is negative 8.901. So indeed, these are different models. So, and we can look at that in VMD, which is what we're going to do momentarily. Okay, so some of the other keywords that you typically want to search for in a PDB file, and also check in a paper, to cross-reference things. I told you sometimes proteins could be missing various amino acids. If there are missing atoms or amino acids in a protein, that's designated in the PDB file with the keyword missing. So if you just search for the word missing, all in caps, you see that there's nothing missing in this file. I'll show you later a file where we do have missing amino acids. But this is always something that you should search for in a protein databank file to see, if there are missing amino acids. And then the next question is, why are they missing, and do you need to worry about them? And that's where the paper becomes important. Were those amino acids not resolved because that region of the protein was too wiggly when they were trying to get the experimental structure of the protein, for example, with X-ray crystallography? Did they get rid of those amino acids for some other reason? It aided in crystallization, for example. And so those are, questions that you need to figure out. And then if you want to have those amino acids back, you need to model them, like I said, back in. Another keyword, again, this one won't show up in here, but I'll show you what it is. We'll see it again later. That often you want to search for, and will, again, usually be mentioned in the paper that is associated with the deposited structure, is to see if there are what are called disulfide bonds in a protein. And so cysteine amino acids can form disulfide linkages with one another if they're close enough. So if we look back at our amino acid page here, cysteines have these SH groups, and so you can form a disulfide bond if those cysteines are in close enough proximity. To find out if there are disulfide bonds in a particular structure, you just search for the keyword SS bond. And again, that is not in this file, but it'll be in the FAEG file that we look at in a little bit. So these are the types of things that you typically want to look for in a protein file before you just blindly set it up in TLEAP and simulate, because you could be simulating basically the incorrect structure with the incorrect kind of bonded architecture. Okay, so what I want you to do now is we're going to visualize this PDB file with VMD. So you can do that one of two ways. You can either SCP or rsync that PDB file to your local machine, or if you have the protein databank page open, you can just go ahead and download it directly to your computer, of course, by downloading the file, PDB format, and that'll download. And then on your local computers, you should all have VMD installed at this point. Is that true? Does anybody not have VMD? Okay, good. So go ahead and open up VMD, and we'll go ahead and take a look at the trip cage structure. Make this a little bit thicker. There we go. Okay, does everybody have this open up on their screen? Okay. So this is the trip cage system. If you look over at VMD, I showed you that in that particular PDB file, there were several snapshots of the trip cage system, right? There were those TUR lines in between the first set of coordinates for the 20 amino acids and the second set. And in fact, there are a whole lot of frames. If you look at the frame number here, there are 38 snapshots that were deposited in that NMR ensemble. So if you were to scroll through this, you would see the various structures that were determined for trip cage in that particular experiment. So what we're going to do for our simulation is we're going to choose one of them. Okay. So let's go ahead and just choose the first snapshot to run the simulation with. So what I want you to do is to go ahead and just go to File, and then Save Coordinates. And then for your selected atoms, you're going to pick all. So you're going to do the whole system. So you're going to save it as a PDB file. Yeah, what's up?
Oh, I'm sorry. My save coordinates button was grayed out.
Yeah, you have to actually highlight the thing in the main window first. Yeah, yeah. Yeah, so you go to File Type PDB, And then here, where it says frames 0 to 37 with a stride of 1, we don't want to save all 37 frames. So just change that last to 0 as well. So this means we're going to start at frame 0. VMD starts counting at 0, much like you've seen with the analysis. It's a 0-based index. Start with 0, end with 0. Stride of 1 means you just are stepping 1 frame at a time. And then we're going to save this. So if you just click save, and then give your file some name. So, tripcage.pdb, and save it. Then you should now have a PDB file that we can upload back to the cluster and start to process and then run simulation with. Okay. Any questions about any of those steps? Okay, good. So let's go ahead and let's take a look at it. So here it's in my downloads folder, but tripcage.pdb. Well, if you look inside of this file, let me increase. There we go. You should now see again. So it starts with residue 1. Here's that negative 8.901 that you remember from the first x coordinate of the first snapshot from the raw PDB file that we downloaded from the protein data bank. So that's a good thing to check. Make sure that after you save it in VMD, it actually corresponds to what you started with. And then if we go to the very bottom, we see that we end with 20. We end with an end line, and there's only, if we scroll through, 1 copy of the protein now in this file. So we've saved just 1 frame of the trip cage protein. Okay. So go ahead and upload that now to the cluster, right? Which you can do with your SCP command. So if you just go SCP, and then what we want to copy, actually, might be easier with just do SFTP and go to your. I just have a keyword here to log in quickly. cstate. So if you SFTP to your account and just put tripcage.pdb, it'll upload it right away. So that's a quick way to upload it to your home directory once you're on the cluster. So go ahead and do that.
Do I have to do that if I'm logged in already, or before I log in? Like I haven't logged in.
So I'm currently on my local machine here, right? Then I'm connecting to the remote machine using the SFTP command. I type, for you, this would be, the SUSE M1 blah 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 at login1. I just have this all aliased. So now I'm connected to Colorado State machine. If I type, so in SFTP, if you type LLS, that's your local list. If you type LS, then you see what's on the cluster. And so all I'm doing is I'm just saying put tripcage.pdb, which uploads it to the remote machine. Or you can use SCP, that's fine. Okay, does everybody have that uploaded? All right, so now what we can do is if you go into the tleap directory in your day7 folder, you'll see a tleap.in file, and you'll see a README file, and you'll see a sample output directory. Okay. So what I want you to do is I want you to move that tripcage.pdb file wherever you put it into this directory as well. So now in this directory, you should have your tripcage.pdb file, you should have your tleap.in file, and you should have your README file. Did you use tleap yesterday with Elijah? Did he have to use tleap at all? He is not. Okay. Does everybody have this directory ready to go? Yeah, so I'm currently in day 7, trip cage, yep, TLEAP. Not into the sample output directory. That's there in case something doesn't work for you. You have a copy of the output that you could use, for example. So, yeah. Okay. So let's take a look inside of this TLEAP. Well, let's do actually one other thing first. So, so TLEAP, I mentioned there's this kind of suite of software called Amber Tools. And so Amber Tools includes things like the CPU version of PMEMD. We're going to use the GPU version of the PMEMD program, which is the molecular dynamics engine, the one that actually runs the simulation. It includes CPP-Trash, which I mentioned is an analysis tool. Includes a whole bunch of software programs. One of them is TLEAP. And so TLEAP is a program that will help you to set up those initial parameter and coordinate files that you need in order to run a molecular dynamics simulation. So let's go ahead and take a look at, just type TLEAP at your directory, and you should get a handful of lines and then a message, welcome to LEAP. Does everybody have that? Okay. And then if you type help, it will list for you all of the possible commands that are available to you in TLEAP. And this is, I just want to point out, we're still using Amber 14. Martin has recently installed Amber 16, so there may be some slight improvements or differences to TLEAP in Amber 16 compared to 14. I'm not entirely sure yet. I haven't looked at it. Actually, Amber 15 tools versus Amber 16 tools. But anyways, so there may be some slight differences in the new version. But again, it should all be documented in the newest version of the manual. So even though in this set of files I gave you the Amber 15 manual, if you're using Amber 16, you should be using the Amber 16 manual to make sure you're using the most up-to-date manual for your software. So all I did to do this is I just, at the command line here, I typed in TLEAP and hit enter. Did that not work for you? Oh, really? Did that work for anybody? Okay, interesting. So what error is it giving you? Okay. That probably means there's something that's not in your path.
Oh.
Let me do something really quick.
Okay.
Were you able to get it to work then? No, it's still not working. Okay. But everybody else is working, just to be sure? Okay. Have you tried typing TLEAP though yet, Matthias?
What? No, the trip case.pdb isn't on my.
Right, but can you try typing TLEAP to see if it works? So because I'm going to send Martin an email to see if he can fix it. So I just need to know who's working, who's not. Works for you. Troy, works for you. Matthias?
I have to be in the TLEAP directory?
No, you can type TLEAP from anywhere. You just have to be on the cluster.
Yeah, it works.
Okay. Okay, so I can so take a look in the tleap.in file. So this is what a tleap.in file that will be processed by TLEAP looks like. So basically, what this is doing, kind of line by line, is it starts with loading kind of the force field that you're going to use, which is going to describe things like the bond strengths, the charges, the partial charges on atoms, so on and so forth, in your molecular dynamics potential, right? So you have to choose some force field, which is going to give you all those parameters, right? Contain all those parameters that are required for running a simulation. Okay. So this first line here, source leaprc.ff14sb, this is a amber force field that contains all the stuff that we're going to need for your typical run-of-the-mill protein. Okay. We'll talk about a little bit when you have special cases. The second line here is loading some other ions parameters that are compatible with the TIP3P water model. And then the next line after this comment, so just like in other scripts, you can add comments. You can do this in your Amber TLEAP script. What we're doing is we are loading our PDB file, and then we have to write the path to the PDB file. For you, this is not going to be the same. My file is somewhere else. Yours is just in the local directory in which you have the tleap.in file, so you'll need to change this path. But basically what we're doing is we're loading a PDB, and we're setting it equal to some variable, right? So you've done these type of variable assignments. In Python, you should be familiar with the syntax. All we're doing is loading PDB U1. When we run protein simulations, you could run it in vacuum. You could run it in implicit solvent. But in order to represent the aqueous environment, we need to solvate it in water. Okay, and so one of the commands to do this, there are actually a couple of commands in TLEAP that can be used to do solvation. Is a solvate oct. This actually creates an octahedron shell of water. So you could do a square box, right? But actually, the octahedron is sometimes useful if you have a protein, for example, that's going to tumble around, and you want to minimize the amount of water that you need in order to accommodate that protein. For example, if you had a long, skinny protein, right, and you put a rectangular box around it, okay, you can imagine that if the protein were to rotate, all of a sudden it can interact with its periodic neighbor. And we talked about periodic images, or Elijah talked about periodic images yesterday. And that isn't really representing the system that you want to simulate in, in your MD calculation. So, what could you do to solve that? Well, you could just make a much larger square box, a cubic box that allows the protein to tumble and not see itself. But a way to achieve the same result and kind of not have quite as many waters would be to make something that looks a little bit closer to the shape of the sphere. And so the octahedral box is one way that you can do the octahedral shell is one way you can do this in Amber. And so this solvate oct command, what it's doing is saying that you're going to create this octahedral shell around what you've loaded into U1. You're going to use the TIP3P water. And 10 angstroms, so this number here is in angstroms, is how far basically you want the boundary to be from the protein atoms. So it's going to create a 10 angstrom octahedral shell of water around the protein. Again, when you actually go into the simulation protocol for your real research projects, you may want to make this a little bit larger to make sure that your protein isn't going to kind of get too close to its periodic neighbor. 10 to 12 angstroms is probably okay-ish for most proteins. If you have proteins that are you expect to go through some large conformational change and change shape quite a bit, you may want to increase the buffer a little bit more. So this is just something that you have to kind of look at the system you're trying to simulate, understand a little bit about it, and even run some test simulations and kind of see, if you need to add a little bit more water to be safe. The next thing that we need to do is we need to neutralize the system. Elijah talked about this briefly yesterday too. The way that we deal with long-range electrostatics in these periodic molecular dynamics calculations is to use a method called particle mesh Ewald, which relies on an overall neutral molecular dynamics system. And so a protein may have an overall charge, right? It's very possible because it's, some of those amino acids, like we looked at earlier, are positively charged, negatively charged. So if those don't exactly balance out, then you're gonna have a net charge on the protein. Counter ions in order to balance that charge. Again, a couple of ways that people do this. One of the useful commands in Amber is to do this add ions rand command. So this will go through, it'll randomly basically delete a water molecule and put an ion in its place. And what this means here is that we're going to use chloride ions, and this 0 means neutralize the system. So add however many chloride ions you need to add in order to neutralize the protein. So how do I know it was going to be a chloride ion? We'll talk about that in a second. But what you need to do is figure out if you need to add negatively charged things or positively charged things in excess, and then use something like this to neutralize. Sometimes you actually want to add an ion concentration that is physiologically relevant. So you may want to add some molar concentration of ions that resembles the experiment that you're trying to reproduce, some salt concentration they've used, or the physiological concentration of a salt in an actual biological system. So in that case, what you have to do is go back to a little bit of your chemistry and calculate, how many ions you need, for a given concentration in a system of a given volume, right? If you know all of those things, you'll be able to back out how many ions you need to hit like a 0.1 molar concentration of sodium chloride, for example. And so you can also do it like that. If you had something like that, what you would do is you wouldn't just specify one ion, you would specify like Na plus and Cl minus, and then give the numbers of each that you want to add to the system in order to get to the appropriate concentration. Of course, you'll need a little bit of excess of one ion over the other in order to balance the charge on the protein, right? But you can hit pretty close to the concentration that you want to be at. The next thing you want to do, I mean, this is for the very simplest system, of course. So these are kind of the very basic steps for a very run-of-the-mill type protein setup. But if you're happy with everything that you've done and you think you have the system you want to simulate, then you get to the point where you save your Amber parameters. And so what we're saying is to save Amber parameter files for the U1 unit, which we loaded in as the PDB, and then we modified in these two ways, by adding water and by adding ions. And then the file names that we're going to use for our output are going to be tripcage.parm7. So this is going to be your parameter file. And T7, which is going to be your initial coordinates. Those are the two things that Amber needs in order to run the simulation. And then finally, we have quit. Yeah, great.
So on this comment in the middle, is it supposed to say, how did I know to add the chloride ion? Or is it supposed to be the sodium?
Yes, that is probably a typo. Okay. We're going to check in a second. So yeah. So yeah. So let's, okay. So how did I know? That was actually the next thing that I was going to ask. So so let's run it interactively once. So let's just let's go and type in tleap again at the command line. And then what you're going to do, let's go ahead and source leaprc.ff14sb. So that's our force field. So you should see a bunch of things where it says loading library. So you're just going to type, let me find my cursor there. If you type that line there, which was just the first line in our tleap.in file, right? Okay. Everybody have that? Yeah, I sent Martin an email. I'm waiting to see if he writes back. So then you'll go U1, or whatever you want to call it. See how names aren't important, right? So don't think that you have to call things like U1 or whatever, right? These are just variable names. Just make them up. Load PDB, And then you have to type in the name of the PDB file that you want to load. I think I put this in here. So if I do that, it'll load my PDB file. It tells me the total atoms in the file is 304. Okay. So I could always go back and check that and make sure everything loaded like I expected, because I could just look at the number of atoms in the PDB file. And then if you type help, you'll see there's a command here called charge. And so what charge will do, let's take a look at it. So there's the command charge. Let's type help charge. And the command, the way it works is you type the word charge and then you type the container. And by the container, they mean that you won, that I just defined. So the thing that has the PDB file loaded into it, for example. If I type charge U1, it'll evaluate the charge of that group of atoms. Of course, if I didn't load the force field first, then it wouldn't have worked, because without the force field, the partial charges on the atoms are not known, right? So that force field is required to define those charges. And so I get a 1 here for that charge. Yeah, Ellery. No, the force field being when I wrote this line up here, source leaprc.ff14sb. That is the Amber force field. And you see that it loaded a bunch of libraries. And actually, if you wanted to, you could go into this directory and you could use VI to look at what these libraries look like. These are going to have a whole bunch of different parameters that define again all of the charges and bond strengths and equilibrium lengths in your molecular dynamics potential that need to be evaluated in order to calculate forces in your simulation. So it tells you the charge is +1. That's how I knew in my tleap.in file that I needed to add chloride ions to balance it, because I needed something negatively charged. So that comment was wrong in the tleap.in file. Okay, so this is a quick way you can see what type of excess ion you need to add in order to set this up. Any questions about that? Yeah, I chose chlorine. Yeah, convenient, typical. I mean, yeah, NaCl, KCl are two of the ones that you use a lot in MD simulation, biologically relevant. Yeah.
Right before it said add ions random. Like if we had to figure out the exact amount that we needed, we wouldn't use that command, right? Because we would have to tell it how many of each.
No, you can still use that command. So let me understand your question exactly. So you're saying that if you wanted to add ions up to some concentration?
Yeah.
No. So then if you wanted to add ions up to some concentration, the syntax for that command would look like Cl minus. Let's say I want to add 40 Cl minus, and I want to add 35 Na plus for some reason. I mean, I'm just making these numbers up. But you can still use the add ions random command. That has nothing to do with only being able to do charge neutralization. That has to do with the algorithm that is used to add the ions, which is to randomly choose some water molecule, replace it with an ion.
And then the system just knows that, like, you rating 40 doesn't mean like you want a total charge of 40. It means like the number of atoms. Because before in the original we have 0 at the end, so it like neutralized it. Right.
So 2 ways you can answer that question. You can either read the Amber manual, which will tell you exactly how add ions rand works. So before you use any command, you should make sure to read the manual and understand what all of the parameters, so all of the arguments mean. Okay, and then if that isn't clear enough, there's a great Amber message board that you can look at as well. The other thing that you can do is you can see how helpful the help for that command is in the tleap program itself. So if I type help add ions rand, it'll tell me a little bit about it, right? So add counter ions in a shell around unit by replacing random solvent molecules. If the number of ion 1 is 0, then the unit is neutralized. Ion 1 must be opposite in charge to the unit, and ion 2 cannot be specified. Otherwise, the specified numbers of ion 1 and ion 2 are added in alternating order. So if you specify them both, so it tells you exactly the answer to your question, right? So that's the Amber manual is actually pretty good in terms of having documentation for all of these commands. So I would suggest looking at that, and then also looking within tleap itself. Yeah, Ellery. Okay. Any other questions about that? Okay, good. So let's get on to the part where we're actually going to try to set up this simulation now. Okay, so you have your tleap.in file. Hopefully you have gone in and modified this line to point to where your actual trip cage file is located. So I'm going to modify mine because my file is right here. So just tripcage.pdb. And 1 second here.
And then charge you one line is the next charge for your
Sorry, say it again.
The charge you one line was the thing we did right before this, computes the net charge for the whole booking.
For whatever is in U1, in that variable U1. Yep, yeah, exactly. Okay, so then if you just type tleap minus f tleap.in, and then we're going to go ahead and redirect the output to a log file. So if I do right caret tleap.log, hit enter, let that run. It'll run quickly. And then in your output directory, you should see the tripcage.parm7 and tripcage.pdb files. Let me check something really quick. Okay, so Greg and Josie, can you take a look at your .bashrc files really quick? We're going to see if we can get tleap into your path. So if you do vi tilde.bashrc. Actually, never mind. It looked like Martin already changed it for you, Josie. So see if tleap works now. If you type. It's still command not found. Try doing that. Try typing source and then tilde.bashrc and hit enter. Try bash profile. Tilde /.bash profile. Sorry, not vi, but source. Yeah. It's up here on the screen, so the same one that is that what you typed? Maybe with the word source. So tleap's still not working?
Oh, no.
Now it works? Okay, good.
Well, I changed your bash profile.
Okay, so does everybody have the, except for I guess Greg at this point, the tripcage.parm7 and tripcage.rst7 files created? Okay. So those are your parameter and coordinate files. Again, those should be similar to what you were doing for benzene the other day, so we won't go into these in a lot of detail. But if you use VI, for example, to look at the parm7 file, it has a lot of information here about atom names for all the atoms in the system. You can scroll down and look through this. So here are all the waters. It has information about all the charges for each of the atoms, so on and so forth. So this stores a lot of the information you need to run the simulation. And the tripcage.rst7 file then has your coordinates for all the atoms in the system in the same order in which you find them in the parm7 file, because those orders need to correspond. Okay, so once we have those files, we can actually start running a simulation now. So if you go back to the run sim directory, okay, you'll see that I've organized the run sim directory. So this is in tripcage/run sim into 4 subdirectories. And so you talked about several of these phases of simulation yesterday with Elijah, energy minimization, equilibration and production. For this protocol, we're adding one additional stage, which is going to be a heating stage for the simulation. And this is to gradually increase the temperature of the system instead of cranking it up to the target temperature immediately, which is a kind of typical protein simulation protocol. Okay, so the first thing, of course, you want to do is you want to perform your energy minimization, as Elijah talked about yesterday. This is, primarily for protein simulations purposes, to make sure that there are no bad contacts in the system initially at the first kind of step of simulation. What do we mean by bad contacts? We mean the atoms that are like way, way too close to one another, so that if you were to go directly onto dynamics and start calculating forces, you would run into trouble because you would have enormous forces because you have atoms that are sitting on top of each other, which could lead to gigantic accelerations, which lead to velocities that are way too large, which then lead to your simulation failing. And so minimization is a way to kind of energy minimize the system and get to at least a local minimum in energy where we remove some of those bad contacts. But let's look in the min directory. Okay, so if you go into the min directory now, you'll see two files, and so we're going to do a two-stage minimization. The first one is called min.1.in, and the second one is called min.2.in. If we look inside of min.1.in, you'll see a lot of the same parameters that you saw yesterday. So I'm not going to go through these in great detail. Like I said, one of your pieces of your homework assignment will be to go through these and actually figure out what each of these flags are doing based on the Amber manual. But there are a couple of extra lines here that I want to point out. These are restraint lines, which you didn't use yesterday system. And so what the restraint lines are for is, when we typically set up a protein simulation, we have that nice structure of the system. And then, it comes from some experiment, so we believe that it, corresponds to reality in some way. And then we put this completely kind of fictitious group of water molecules in an octahedral shell around it, and we throw some ions in there randomly. So, what would be nice to do would be to kind of let the water and the ions equilibrate while we are keeping the protein somewhat close to its original structure, right? And so one way that we can do that is we can put some restraints on the protein, which you can think about as just extra little harmonic springs that are referencing the protein's atomic positions to some reference structure, right? Okay. And so now the atoms in the protein can't move very far away, for example, from their initial positions if you use the initial positions as the reference structures, because each of the protein atoms is tied to that initial coordinate by a little harmonic spring. And so the way we can do this is using the mask notation that's built into Amber. You'll see this with CPP trash as well. So I can define what is called a restraint mask. Again, this is in the Amber manual. So if you look in the Amber manual, there's a section on how to make atom selections using masks in Amber. So what this colon means here is it means residue. And the statement is I'm going to choose residues 1 through 20. Okay. So those are, as you remember, triptase is a 20 amino acid protein. So those are all 20 amino acids of triptase. And then I'm choosing these 4 atoms, Ca, Co, and N, which if you look back in your PDB file, or if you were to open up in BMD and just show those particular atom names, you would see this makes up what's called the backbone of the protein. And so these are the common piece of all of the amino acids. Amino acids have a backbone group of atoms and then a side chain being the group that gives that amino acid its chemical specificity. And so what I'm doing is I'm restraining the backbone, basically. And so this here is also an example of how you can do comments in Amber later on. So all you have to do a comment in one of these input files is you write an exclamation point after your comma, and then you can write some text after that. And so this is what you'll be doing later. This restraint weight column then says what is the spring constant that I'm going to use to restrain those atoms. And so, you know, typical value you might choose for this is about 10 kcal per mole angstrom squared. And so this is just the weight, the stiffness of that spring. If you make it very loose, the atom, of course, will be able to wiggle more. If you make it very, very stiff, it's going to be much, you know, much more stuck in place. Okay, so let's go ahead and run this. So if we run this first stage of minimization, we can do that with this run.1.sh file. So this is one of these Slurm submit scripts like you used the other day for your benzene simulations. And so, but now the difference is before you were, well, actually I think yesterday you ran on GPUs as well, right? So you've already run on GPUs, so we don't need to go into that. But for minimization, we're actually going to use the CPU version of PMEM, which is a bit better for numerical accuracy. And so this command should just work, but just to go through it, so you're reading in your min.1.input file, you're producing a min.1.out. You're going to create a restart file. This -x would create a coordinate file, but actually the way Amber's PMEM program is built, it doesn't create coordinate files, trajectories during minimization, only during the other dynamic portions of simulation. If you are ever running into trouble with minimization, like something is crashing and failing, and you want to produce the trajectory file to see why, you can go back and instead of using PMEM, you can use another Amber simulation tool called Sander. And Sander actually will allow you to output a trajectory during minimization as well. So you can try to figure out the details of what might be failing by using Sander instead of PMEM. And then this -c is what we're going to use for the initial coordinates. So you're going to have to change that because your RST7 file is right in your current directory. So you'll have to change, you know, where this is pointing to, and you'll have to change where your parameter file is pointing to, I think. So check that. And then the reference file. So this reference file is because this is something new that you didn't have in your inputs yesterday. This is because we're using restraints. So this is the flag, the command line argument that we give to pmem or pmem.cuda, pmem.mpi, whatever, that says we are going to be using restraints in our simulation. So this is the file that I want you to use that defines the coordinates to which I want you to restrain the atoms over the course of the ensuing simulation. Yeah, Matthias.
So even though I'm calling upon the triptase, the RST7 for the coordinates and the restraints are in it, we need to specifically say like ref to refer to.
Absolutely, right? Because you may want to restrain the coordinates to some other completely different structure, right? There's no reason necessarily that you should add restraints relative to the initial structure. Let's say that you want to drag the system from one structure to another. So your initial coordinates are the -c. Your reference coordinates you want to drag it to are over here somewhere, right? So then -ref could be that, and it pulls the system over there, right? So that's why you want to have two separate command line arguments for that. So those, in principle, can be two different files. Yeah. So it makes sense? Okay. Any other questions about that?
Just so happens that we're not doing any of that.
Yes, right. Because what we're saying is that we don't want the structure to move very far from its initial structure. So that's why the ref file is the same as the initial coordinate file.
Skip the first like lines with all the coordinates just because it's looking for the restraint. Like since we're calling it like the ref command, it'll skip all.
It's not a command; it's an argument, right? So yep.
It'll skip all the lines that are saying the coordinates and just look for the restraint line in that file. The rest of the lines won't affect it at all.
I'm not sure what you mean by that. So, I mean, all the ref flag says is it says that is the file that follows that is the file that's going to be used to define the positions to which the atoms are restrained over the course of the simulation. But I'm not sure what lines you mean that are being skipped. Okay. Yeah, we can talk about it later if you want. Okay, so now if you just type sbatch run.1.sh and hit enter, I'm not going to do it because I don't want to take up the GPU. But if you hit enter, it should submit the job. It should not fail as long as you've pointed everything to the right directory or paths. And now if you type the word SQ and then -u and your username, you should hopefully see your job in the run state. So look up Rebecca's, for example, not on there yet. Look up Troy's, not on there yet. Does anybody have theirs submitted yet?
Cluster's really slow. Yeah.
We have to.
I just ran mine, so it should show up.
Is your username BriarT1?
No, no one.
What is it?
No one.
Okay. So type ls and see if you have output. If you do, then there may have been an error. So you need to see what that output is. It may have gone into the queue and then died immediately. Which it shouldn't have.
Would it be in the output folder or just?
No, it should just be in the regular folder. I'm going to run it. Mine is running. If you type ls in your directory, do you see a job.1.out file? No. Okay. So SQ minus U.
Yeah, no, I'm messing with that.
Okay, so you have it working. Everybody else, do you have it working?
Yes.
Okay, good. Working? Okay. Thanks. Okay. Josephine, Greg, is it? Okay. So it's a path problem, so, okay. So this simulation should be very quick. Should run in basically about a minute once you get it submitted. It's just 5,000 steps of minimization. That we're simulating is very, very small. In fact, if you were to look in the tripcage.parm7 file, at the very top, this first number here is the total number of atoms in the system. So there's only 5,771 atoms in the system. So it's a very small system. It'll run very quickly. Okay. Once it runs, you should have a min.1.out file. And you looked at these output files yesterday, which has a lot of information about the various energy terms that are being calculated over the course of the simulation, how much restraint energy there is due to the restraints that you added to the system, so on and so forth. And then hopefully, if it runs and completes successfully, at the end, you'll get some information about how much time it actually took the simulation to run, and some other statistics in terms of your final results, the fact that you reached the final step of simulation. So you always want to check that at the end of your output file, that it didn't prematurely fail for some reason. It'll either not get all the way to the end, or it'll report some error message if that's the case. And Amber error messages are typically quite good, so they're usually easy to figure out what they mean. If not, there is somebody else out there in the world that has run into the same error message. So if you copy the error message from the file and paste it into a Google search window, somebody on the Amber message board has probably asked about it. So you can typically find answers to most things on the Amber message board. Also, if you ever can't find answers to questions on the Amber message board, it's a very friendly community. So if you sign up for it, you can post there, and Amber developers will respond usually fairly quickly to folks that have questions. So that's another useful resource. Okay, does everybody have their minimization run? Is anybody still waiting for it to finish? Okay, we're good? All right. You haven't done yours yet? No.
I'm just struggling with where to
Okay, so what is your min.1.inf or your in your run.1.sh file? What does it look like? Yeah, so you mean everything to point, meaning these directory paths?
I mean, like manually looking at it, that's fine, but when I run stuff, it doesn't.
So yours is still not working? Okay, let me take a look at this. Yeah.
Should we go ahead and run the second one?
Yeah, if you know how to do that, you can go ahead and run the second one. So, no slash there, right? Yeah, because that first slash is saying that it would be like a root directory or something.
Oh, yeah.
Yeah. So get rid of those slashes.
You take away.
And yep, get rid of that one. And I think that you should be okay this one. So take a look.
I guess.
So let's see where you're at. So type ls. Okay, type ls space // td.
You have to change.
Yeah, because you don't have the files in there yet. So did you ever probably because you weren't able to run the td. Right, go ahead. So go back to that directory. That tlead directory. So just go back one more directory level. Tlead directory. And then bi the tlead.in file. Let's take a look at it. And get rid of that // because actually tripcase.pdb is in the same directory that you're currently in. Yeah. Save it quick. Okay. Now to run it, type tlead space -f, which will tell it to read in the file, space tlead.in, and then space, and then do a right caret because we're going to redirect the output to a log file. So right caret, yep, and then space, and then type in tlead.log, and hit enter. That should run. Now if you type ls, then you should see if you have the farm7 and rc7 files there. So those are created by that tlead script. So now you go back to the minimization directory and do sbatch on your run.1.sh file. It should run. Yep. Okay. Yep. This one's our.
This one doesn't have a like, oh, my TV, it looks like I have all files there. Most of the examples are all by SBatch.
You just hit one a bunch of times and then you sign down. I don't know exactly what it does. Multiple ones. Yeah. Multiple ones.
So do SQ minus U and then your name.
Not like on line.
Type ls.
Control B goes up.
Uh,
It's like a page up.
So do vi run.1.sh. Were you able to run things yet? Yeah.
I'll be here all day. I'll be here all day. I don't understand how
But I
that
understand why it's not.
You should be still working on something Thursday.
You're like
I'm saying not cool. I'm saying you're so
But
not
she's
cool
still-
that it's
she's
so
still-
slow.
she's still
it's
pretty
at
that
least
whole
supposed
world.
to drop that one out. It fails. So it seems like it's
Super small, but it's can handle.
This problem the other day with the issue that I was on. No, it's just.
Did you not have coffee today?
They did. Well,
So that's possibly still the case. Yep.
Drink it once, you get independence.
Okay. Yep. Yep. So move everything over to the cluster directory.
I used
Okay.
to see that. I used to see that. When I do, you know, do that.
Okay. So. All All right, you're okay if we push on a little bit, or you'll, okay, awesome. So you've run the first stage of minimization. What you should get as a result is you should get that min.1.output file. Like I said, you should check and make sure that that indicates that everything is completed successfully. Look at the end of the file, see that you get all the timing statistics, everything is there. The min.1.rst7 file should be your minimized coordinates now, which we're going to use as the input coordinates for the second stage of minimization. If you want to take a look at the min.1.rst7 coordinates and see what moved, right? So if you actually wanted to visualize it, you would have to look at that file using VMD. Now, the way that Amber writes out this RST7 format, VMD doesn't, because we're not using the ASCII version anymore, we're using a, if I VI this file, you'll see what I mean. Well, actually, mine didn't produce anything yet because I killed the simulation early, but let me go into my pre-prepared output file. I'll show you what I mean. We are writing the output in a binary format instead of in an ASCII format. So if I were to try to look at this with VI, give this a second to load up. Oh, no, okay, so actually I guess I did keep this in ASCII format. Okay, so you could visualize this with VMD then directly. If you get the RST7 in Amber's restart binary format, you actually have to do one conversion step to make it VMD readable. And so you can do that with CPP trash. I'll show you that tomorrow when we do some CPP trash analysis, but this is fine. So you could look at that in VMD. You could load both the initial snapshot and the minimized snapshot, and you could toggle the VMD, slide bar back and forth to see what had moved in between those two snapshots. So you should try that on your own time. Okay, so what do we do then to go on to the next stage of simulation? Well, we can do that with this .2.in file. You see everything in here is basically the same, except what I've done in this stage of minimization is I've gotten rid of the restraints. So now I'm just going to let everything in the system minimize just a little bit, okay? And so for another 5,000 steps, bless you. And so we can do that with the run.2.sh file, okay? And so again, we have another pmem.mpi command. Now we're using min.2.in as the input. We're writing min.2.out as our output. We're writing min.2.rst7 as our restart file. Again, this isn't actually necessary because we're not going to get any trajectory produced by pmem for minimization. We have -c for the coordinates now points to min.1.rst7 instead of the original tripcage.rst7 file, because now our initial coordinates are the last frame of the previous simulation, right? So we need to restart from there. And then again, our parameter file, and actually this is a mistake, this reference isn't here because I don't have any restraints in this stage of the simulation. So I can take that out. And then you can run this again with sbatch run.2.sh. And so what you should get now is another round of minimization that comes out of that. Yeah, Troy.
If you run it with the reference flag, does it do anything? Or?
It probably crashes. It probably says that you're trying to run with the reference, but you haven't specified restraint mask. I don't know that for certain. Maybe Amber.
It looked like it rained.
Yeah, so it may only catch it the other way. Like if you tell it that you are going to use restraints in the input file, and then you don't have the flag, then it crashes. But yeah, yeah. I mean that's good and bad, right? So because later on when you're trying to like backtrack, what happened, you want to make sure these are as precise as possible to what was actually used. Yeah.
So I'm getting MPI initialization.
Okay, interesting. Did anybody else get that? No, I wonder if that's something else that's missing in your path then that may be.
Yeah, it's.
Huh.
It says, sorry, you were supposed to get help about something, but I couldn't find the help file. And it's repeated.
Oh. Okay, can you cut and paste that error and send that to Martin? He fixed that for me actually last week.
Oh, okay.
So yeah, send that to him. I'm sure he can get that quick. Yeah. Okay, so run the second stage of the minimization. And then you should now have, at the end of that, you should produce your min.2.rst7 file at that point. Okay. And then again, you'll get an output file, a second output file. There's also a lot of useful stuff at the beginning of the output file, actually. So just to kind of point this out while you have things running, it gives you a complete record of what the files were that you used in order to run that segment of simulation. So it tells you the names of the files that you used. It tells you the parameter, where the parameter file was, so on and so forth. It also gives you a record of the input file that you use. So if you lose that input file for some reason, as long as you don't lose your output files, you have a record of what went in there. So that's actually also very useful. It gives you some other information, like the header from the parameter file tells you the number of atoms that were in the system. All those other variables are listed as well. Tells you the type of box that you're using, this truncated octahedron. Gives you all of the other flags that actually are included in the simulation. So one thing you'll find about Amber as you're going through the manual is that you set flags, but there are also a lot of default values that are set in Amber as well. And so this will list not only the things that you've set by hand, but the default values for other parameters that are the the default switches that Amber uses behind the scenes for the simulation. And then eventually you get to the results section, and that's where you're given your step and your energy. One other thing that I'm doing, just to point it out in this minimization file, is I'm outputting energy information every single step. These output files, they're not huge, so sometimes that's nice. You can typically write out the energy output much less frequently than that. But if you're trying to catch like an error or something in particular, sometimes it's useful to write out the energy every single step so you can see where things are crashing. If there are certain energy terms that are going to infinity, you'll notice that because what will happen is instead of having a number here, it'll be all asterisks. And so what that says is this number is crazy large. And so that's sometimes okay at the beginning of a minimization because, like I said, you could have bad contacts at the beginning where things are too close. If that starts happening at later steps in the minimization, sometimes that means there's a problem. Sometimes that's about the point where your minimization crashes. And so so that's something useful to look for as well. Yeah, Greg, did you have your hand up for a question, or was that?
I moved my min.2.rst file to see if I could visualize it, and it like loaded it. Like I checked the file and it says it has all the coordinates, but on VMD there's not.
Yep, exactly. So did you load the parm7 file first?
Oh no, I didn't.
So two things you need to do. So in VMD you have to load the parm7 file first, because that's going to tell VMD how to interpret then the coordinates that you load into the file afterwards, right? Because otherwise all VMD has is a list of numbers, right? It doesn't know anything about what type of atom it is, how to represent it visually within the visualization software. If it's a carbon alpha, then it's going to be a sphere of some certain size and color, and so on and so forth. So you have to load the parameter file first, then you load the coordinates into that parameter file as the second step. Okay, so let's go ahead and talk about these other stages of simulation. You can run these. We'll take a look at the sample output for now because we're getting pretty close to the final time. There's a couple other things I want to talk about. So you can run these and see that they work. I'll be around for the rest of the day, so you can stop by the office that I'm sitting in next to Martin's office and ask questions if you want. But let's just go through the overall protocol. So the next stage after minimization in a protein simulation, typically what you want to do is you want to gradually increase the temperature of the system. And we'll also typically do this in two phases, okay? We'll do a phase in which we're using the constant number, constant volume, constant temperature ensemble. And then another phase in which we use the constant number, constant pressure, constant temperature ensemble. You want to start off at low temperatures, typically with NVT, because the using a barostat, so pressure regulation, at very low temperatures can actually lead to large instabilities in the system. So if you start at constant volume and then switch to constant temperature after about a temperature of 100 K or so, you're typically in the clear. The point of this whole kind of piece of the simulation is to equilibrate the temperature up to about 300 Kelvin. You might have other target temperatures, 310, for example, for like actin simulations I've done in the past, is something we typically use because it's closer to the cell temperature that those filaments operate in. But you pick some target temperature, and you're going to get there in 2 different steps. So let's take a look at these input files. So this is the first heating file, and you see there's a lot more stuff in here. A lot of the stuff you'll recognize from yesterday. So first of all, this isn't a minimization run. So we'll turn that off. That's actually the default behavior, but put that in there explicitly. We're going to read coordinates from a restart file. And then we're going to write our final coordinates and velocities in what's called this netcdf format, which is a binary format. That's so the trajectory files are going to be smaller than they would be if we used the ASCII format. So it saves disk space. That's for the restart file. This iout.fm is the one that says now the trajectory is also going to be in binary format. So this is for restart, this is for trajectory. We don't, as Elijah pointed out yesterday, have any velocities from the end of a minimization run because we're not doing dynamics. And so irest is equal to 0. We're not getting velocities from the initial coordinates. We're just getting coordinates from the initial coordinate file. So later on, we'll change this value because after we run dynamics, we'll have velocities associated with all the atoms as well. This is how often you write restart files. This is how many steps of simulation you want to run. Again, this is probably shorter than you would typically do for a standard simulation. This is the time step that you're taking. Yesterday, it was pointed out that you can use a 2 femtosecond time step if you also use shape to restrain your hydrogen bonds so that your hydrogen bonds are fixed, right, in your simulation. These are printing commands. This is your cutoff for non-bonded interactions. Again, 8 is kind of the amber default. You may want something larger than this depending on exactly what you're trying to do. This NTV equals 1 is what sets up the constant volume simulation. Okay. And then we're saying there's no pressure control. The thermostat that we're going to use to control the temperature is going to be the Langevin thermostat, so that's NTT equals 3. I think you talked about Langevin thermostats yesterday. Frequency of collisions. Your random seed, I'll come back to this row in a second. Random seed, again, now we're turning on restraints. So during the heating phase, we again want to put some restraints on the protein backbone so that while the water and the ions and even the protein side chains are moving around a little bit, the backbone, that structure of the protein stays pretty stable until we're sure that kind of everything else in the system is how we want it to be. And then this NMR opt equals 1 command, what this allows us to do now is to use this syntax down here. And so this is one way that we can increase temperature. So if you have NMR opt equals 1, you can add another section below the control section of your simulation. So up here, this is all of the control section. And now these are where we can change some weights. And so what we're going to do is we're going to change the variable temp 0. We're going to start at step 0, right, which is where our simulation starts. And then we're going to continuously change the temperature until step 50,000, which is the maximum step that we're going to go to in this simulation. And what I'm going to do is I'm going to change temperature 0's value from 0 all the way up to 100. And so it's 0 to 100 Kelvin. And so this is the heating part of this heating phase of simulation, is we're going to just basically ramp up the temperature. So, yeah, question?
Good question about like, heating process. So you're taking, like, because the first minimization was essentially stationary, so it's like 0 Kelvin. a way to slowly
ramp up the amount of kinetic energy that's.
to the actual.
Exactly. Yep. Right. So that way, I mean, if you kick it with a lot of kinetic energy right away, right, those velocities initially are randomly assigned, like we said, Elijah said yesterday, from like a Maxwell-Boltzmann distribution or something. So all of a sudden, I mean, those random velocities are pointing just in every which direction, right? So this is a way to kind of, right, not perturb the system too quickly early on. Let it gradually, get up to the temperature that you want. So you don't have things that are moving too fast too early, leading to things like, too large forces, simulations failing, stuff like this. So that would be the first phase. Now the second phase, so like I said, you can run this in a bit. These all run very quickly. The second phase, you'll see that really the only thing that we changed are these NTB, NTP options. So now we've said we're going to go to constant pressure simulation. Okay. And we've done that combination of setting NTB equals to 2, NTP equals to 1. And then we've chosen the particular pressure algorithm, which Elijah also mentioned yesterday, the Monte Carlo barostat, by setting barostat equals to 2. Everything else is the same. And then down here, we've also changed the temperature value 1 and value 2. We're going now from 100 to 300, where 300 is the target temperature that we want to eventually hit in this particular simulation. Okay. Any questions about that? So what you would do, yeah, go ahead, Ellen.
Is it typical to do like a 2-stage heating process with the second one that's then constant pressure?
Yes. Yeah, that's like a fairly typical protocol. So again, depending on the exact system that you want to look at, especially if there have been simulations done on that system before, you'll want to see what protocols were used there. If there was some particular reason they chose some other protocol, but at the end of the day, what we want to get to is an equilibrated system. So the density is equilibrated, the protein hasn't fallen apart. So there's some kind of like sanity checks that you can do later on. And, a lot of these details of the exact kind of recipe that's used early on, after you've equilibrated for a while, shouldn't matter, right? It shouldn't matter. This is kind of a preparation phase to just make sure that things don't fall apart early on, is one way to think about it. Okay, so you would run both of those, and actually, if you look inside this run.sh file, I've set this up so that these are just both run in sequence right after each other. So there's no reason that you can't just say in a single SBatch file, pmem.cuda, and have your first heating simulation run. And then after that runs and finishes, the second pmem.cuda command will be the next one that the computer executes. And so then the second one will run as well without having to submit a second job. So you could put a whole list of simulation commands in this file. And as long as they can all be completed within the time that you've asked for from the queuing system, which is up here 48 hours, right? I mean, these simulations are each going to take about 5 minutes or something like that, so that's fine. We have plenty of time. As long as they each can finish, then there's no problem with having multiple commands within one. That's perfectly fine. In fact, in some queuing environments, that is probably preferable. Either figuring out how much simulation you can run that takes 48 hours, or to have a number of small pieces, small fragments of simulation you run within one file that goes up that amount of time, because you may once you get access to a resource, you may not want to use it quickly and then have to wait in the queue again to get access to that particular GPU or set of CPUs the second time. So as much as you can run once you actually are in the queue and in the running state, you want to run as much as you can so that you don't lose access to that resource and have to wait in line again. Okay, so that'll produce, again, a very similar output to what you had before. It'll produce a trajectory this time, a .nc file, which is binary format trajectory for Amber. So you could download this file to your local computer, and you could load it in VMD. Again, you have to load the parm7 file first, and then load this NC file into it. And what you would do if you did that, what you would see if you did that, is you would now see the trajectory and all the atoms moving around in your two phases of heating. Okay, So then after this phase, another phase of simulation that people typically use for protein simulation is what's called a restrained equilibration. We are now at our target temperature, and so I've added a line that says temp 0 equals 300. And the reason I put that in explicitly is because the default temp 0 for amber is actually 298, so it's a couple of degrees Kelvin below 300. So I'm explicitly saying that I want to hold the temperature at 300 degrees Kelvin here. You know, everything else, if you look at it, is going to be fairly similar to the previous files that you had. We're still doing constant pressure simulation using the Monte Carlo barostat, and we still have restraints, and my restraint rate weight is still 10. So I'm going to run that, let that run for a bit. Let's look at the second equilibration file. So I have several stages here. Everything, if you look at this one compared to the last one, it's exactly the same, except I've made the restraint half as large. And so now what I'm doing is I'm gradually releasing the restraints on the backbone of the protein. I'm going to gradually reduce them to 0 so that the protein backbone can wiggle a little bit more as the simulation carries on until we get to the point where I'm going to release the restraints entirely, and then I'm in my full kind of production phase of simulation at that stage. So this is a restrained equilibration where we're gradually reducing the restraints. If you look at the last stage, part 6, you'll see that the restraint weight is now 0.1 kcal per mole angstrom squared, so a factor of 100 smaller than it was initially. And then what we'll do after this is move on to the production phase. And so, you know, again, the exact recipe that you use to do this, you know, it's the recipe that makes sure that your system remains fairly stable over the course of simulation. You can, of course, monitor that, again, by downloading all of your trajectory files, loading it into BMD, and doing things like calculating the root mean squared deviation of the backbone coordinates and see that it's kind of leveling off at each stage of the simulation. You've talked about RMSD so far, I think, right, at some point? Yeah, so you could do stuff like that to look at the stability of the system. You could extract other terms from the output files. So, you know, I showed you in the various amber output files, you have the energies, you have, for example, like the total potential energy, total kinetic energy of the system, you have the system temperature. You can make graphs of all of those, make sure that those are leveling off to where you expect they're supposed to be. So there's a lot of checks that you can see that various energies or structural properties of the system are converging, are equilibrating over the course of your MB run. Now, once you've run your equilibration, like you said, the last step will be this production step. Actually, let me show you one more thing in the equilibration file, because again, in this run.sh file, I have written in such a way where all of the equilibrations are run, but I've actually done it using a bash for loop. And so you've done for loops in MD analysis. We'll be looking at it in VMD's TCL scripting language tomorrow as well. But you know, you can also do this in bash. This is one of the bash syntaxes for a for loop. So I'll show you what this is doing. The first line here is just reading in your first equilibration file, writing out your first equilibration. So this is one reason I like to name my file something like name.number.extension. And you can, you know, feel free to be much more descriptive with these names than I am. You know, you can write the name of the protein that you're simulating, the fact that it's an equilibration, whatever. But I like at some point right before the extension to have a number. I'll show you why in a second. Minus P is the parameter file. The beginning of equilibration is going to reference or is going to use the coordinates of the last stage of heating, right? So this has to point back to those heating final coordinates. This reference file, because we're still using restraints, is also going to point back to that same set of coordinates, right? Because we're restraining it now to wherever the end of that previous heating was, the backbone of the protein to wherever they were, wherever those coordinates were at the last stage of heating. And then we're going to write a new restart file and our trajectory file. You'll notice that these arguments are all in a different order than what I had previously. The order doesn't matter. So the arguments just need to be there. But then inside the loop, what I'm doing is I'm defining a variable, and so this is the way that we can do this in Bash. This variable is just equal to I minus 1, so I'm going to go from now 2 to 6 because I had 6 stages of equilibration, right? So if j is equal to I minus 1, then when I is equal to 2, j is equal to 1, right? And so then my pmem-cuda command now, in order to do the next pmem.cuda run, I need to have an I here because I want to run the second input file, right? So I in this first iteration through the loop is 2. So this is going to be a 2. I want to write a new output file. So that also needs to be I because that needs to be 2.out. The parameter file doesn't change. It doesn't have any index. The coordinates that I'm going to use need to be j because I'm using the coordinates from the end of the previous run, right? Which is the .1.rst7. So that's why I've set up this j is equal to I minus 1 variable. And now I have equal.1.rst7. Again, the reference also refers to the end of the previous stage. So I need to have a j there. The restart file is the new restart file that I'm going to produce at the end of this run. So now I'm back to I. And then the trajectory that I'm going to produce is the trajectory that corresponds to the current simulation run. So again, I have I here. So this is a way that you can just loop through within the submit script itself, and you don't have to set up a separate, run.1, run.2, run.3, run.4, run.5, run.6. You can do it like that too, and you can submit them all into the queue. And you can actually, Slurm has what is called dependencies. So you can submit a job and say that it depends on the successful completion of another job. When you do use the sbatch command, you give some extra flags that reference the job ID that you want that particular job to refer back to. So that's another way you can do it. So there's always many ways to kind of set up these job workflows. This is one that's also particularly useful. Okay, so let's look at the last stage of simulation, which is production. So finally, in the production simulation, this is going to be exactly the same file as we had for the last stage of equilibration, except there's no restraints anymore. So we've gotten rid of the restraints now. Everything in the system is allowed to just do what it's going to do under Newton dynamics. And so now, if we look in this run.sh file, again, this looks very similar to the equilibration .sh file, except now I have my first production line, which refers back to the end of the last stage of equilibration. And then I have this loop because I want to run it 10 times. You could run it however many times you want, as long as it fits into the 48 hours, to get as long of a simulation as you want. The other way you can make the simulation longer is you can go into your prod.in file and you can change the value of nstlim, which is number of steps. Currently, it's 50,000 steps, so it's 100 picoseconds. So if I run it 10 times, then it would be a nanosecond of simulation, right? So I could make this longer if I want my simulation to be longer, so on and so forth. So here you'll loop through this 10 times. You'll get 10 different trajectory files. So you may say, why don't I just run one simulation with 500,000 steps? Well, you could do that too. And for this size system, that wouldn't be an unreasonable thing to do because the output trajectory file that you get wouldn't be ridiculously large. But let's say you have a very big MD system, right? And you want to simulate that system for a microsecond of time. And so you want to do many, many, many steps of simulation. You probably want to chunk that up into smaller pieces for various reasons. So things like data management, things like data file corruption. If you only lose a single file, along all the little pieces of simulation you're writing, that's better than getting, having a file get corrupted and you lose the entire microsecond of simulation. So the typical MD protocols we use are ones where we make use of the fact that we can write these RST7, these checkpoint or restart files, and we can do a lot of little pieces of simulation, so the file sizes are manageable and so on and so forth. Okay, so any questions about any of that MD kind of workflow? Okay, so this is typically what it looks like for your very standard run-of-the-mill protein. So I want to talk just briefly about trip gauge system. So what you should do with trip gauge, FAEG system. So for trip gauge, what you should do is you should go through the trip gauge system, and you should run the rest of those pieces of simulation and see that you can get them to work. Okay, so that's kind of part one. So just see that you can actually get those to work. The heating, the equilibration and production runs, right? So see if you can get those to run, see if you can download those trajectories and take a look at them in VMD, the .nc files. Okay. So now I want to talk briefly about this FAEG system. And so if you go into the FAEG initial structure system, let's go ahead and take a look at this PDB file, which is called 4wei.pdb. So again, this is downloaded from the protein data bank. If you do /atom, you can search for the keyword atom, which will pop up a handful of times. So if I keep hitting N, that'll cycle through next, next, next. And eventually I get down to the point where I'm going to see the structure. Okay, and here are all of those atom lines that define, again, the amino acids and the coordinates. We also have these aniso lines. Don't worry about these for now. These are unimportant for what we're talking about. But these atom lines define, again, the atomic positions in this protein. I also, in this structure, if I search for het atom, so HET-ATM, and hit enter. What you'll see is there aren't only atom lines, but there are these het atom lines. So these are non-protein things. So in this protein in particular, what these end up being is this protein binds lactose sugar. So these atoms actually belong to a lactose molecule that binds the surface of the protein. You could download the protein databank file and take a look at this in VMD if you care to look at it. So, so sometimes you have other things in a PDB file that aren't part of the protein, right? Here we have some other het atoms, which are water molecules. So these are water oxygens. So this is a crystal structure of a protein that was acquired at sufficiently high resolution that they were able to resolve specific water molecules, crystallographic waters in the protein. Sometimes those water molecules are very important. Oftentimes you'll see a bunch of water molecules around the surface of a protein in a crystal structure. Those, I mean, we're going to solvate it anyways around the surface. Maybe not so important. But a lot of times, especially in proteins that, bind some ligand, there may be interior waters somewhere inside of the binding pocket that actually play a critical role in coordinating the molecule that's going to bind in that region. And so one of the things that you typically want to keep when you're starting a simulation is not just the protein coordinates, but maybe also those specific water molecules, depending on your purpose in running that particular simulation. You may also want to keep this a ligand if you want to simulate the lactose-bound state of the system. If you wanted to simulate the lactose-unbound state of the system, you could delete those atoms. And so, this now goes into more of kind of the choices that you make when you're setting up a simulation. It's not just download PDB file, run through TLEAP, simulate, right? There's a lot of kind of careful scientific choices that you need to make depending on the questions that you're trying to ask. And so, what is a potential problem we could run into here? Well, I told you that this amber FF14SB force field has information about the protein, but do you expect that it has information about every single molecule that I could potentially find in an X-ray crystal structure? No, the answer is no. And so, for example, for these sugars, there are other force fields that you could load in as well in order to deal with sugars. So, for example, for lactose, you can load in what's called the glycan force fields, and glycan force fields are compatible with the amber force fields, which you can read about on the glycan website. Not every force field is compatible with every other force field. They could have been derived in different ways, right, using different approaches. So you have to be careful if you have molecules, small ligands that are in a system, that not only do you need to find some parameters, for example, there may be parameters already developed by somebody out there, but that they're compatible with the other force field that you're using. If not, then you may need to parameterize that ligand yourself and develop those parameters in a way that's consistent with the way in which the Amber protein force field parameters are developed. And Amber Tools has tools, one in particular called Antichamber, which can be used in order to develop parameters for small molecules that are compatible with the Amber force field. So there are ways to do this. There are tools out there to do this. We're not going to go into that in any detail, but just to make you aware that this is something that can be done. So let's look at a few other things in this file. So let's search for the word missing in this file. And here, in this particular X-ray crystal structure, we see this actually comes up, and it says we have missing residues. And here is the list of the missing residues. So it gives you the amino acid that's missing, and it gives you its residue number. And so we're missing amino acids 9 through 21. If you remember when we looked at the first atom entry, the first residue number, I'm not sure if you paid attention to it or not, but it was 22. This is basically, these are amino acids at the N-terminus of the protein. So proteins go from the N-terminus or the amine terminus to the carboxy terminus, the C-terminus of the protein. So starting at the N-terminus, so we're missing some amino acids. You may or may not want to model these back in. Sometimes the N-terminus is just a large, kind of disordered floppy region that we don't care about. Sometimes you may be interested in it. So again, this is something you want to kind of think about, for your particular problem. But here, we see we're missing amino acids 73, 74, 75, 76, and 77. So let's go back down to the atom section. So if we just scroll down a little bit, and let's look for amino acids. So here's 71. And then if we go down a little bit further, we see 72, and then we go to 78. But let's see how much farther we go. Well, it's 78. I mean, there's a lot of amino acids in this protein, right? So that missing region, that's right smack in the middle of the protein. So if you were to just throw this into TLEAP and create a parameter file for it, TLEAP would create one peptide over here, right? One protein piece, 22 through 71, and then it would create another one over here, and they would not be linked together, or they would be linked together by a very long bond if you didn't realize that you had missing atoms. Your minimization would pull them together, maybe, but you would be simulating the wrong protein because you would be missing 5 or 6 amino acids right in the middle of the protein. So you always want to look for these missing amino acids, figure out, are they just on the periphery and, at one of the terminal ends, maybe we don't care about them. If they're on the interior, that can be very important. And so there are ways to deal with this. Let's search for SS bond. This actually is not, I guess I misremember that, in this protein either, but that again, like I mentioned, defines disulfide bonds in a system. And so this will be part of your project for today, will be to deal with a couple of proteins that have disulfide bonds in them. So you're gonna have to modify your tleap.in files a little bit to get that additional connectivity for the disulfide bond pieces. So anyway, so this is what a protein looks like that has some missing structure. Like I said, I wanted to show you briefly, model it, and then I'll talk to you about the project just for a minute. So if you ever need to model back in missing protein structures, there is a Python program called Modeler, which can be downloaded off the internet and installed, that will allow you to model back in missing amino acids. You can't do 30 amino acids with Modeler unless you have a template structure to which you are trying to produce or assign the secondary structure of your missing amino acids to. So if you have some homology model, you've done a little bit of homology modeling, I believe, Josie, right? So you know that you have a template structure and you have a sequence that you don't have a structure for, and then you try to build based on sequence similarity, sequence identity, the structure of the unknown protein based on the template model, right? But if it's a few amino acids, like it's 5 or 6 amino acids, you can stitch those back in with Modeler. That's likely just a disordered kind of loop region, something small. So the way that Modeler will work is it has a Python script called getSequence.py. So all you would do, and again, we don't have this installed, so you can't actually run it, but I just want to kind of show you what the workflow looks like. You would type in the name of the PDB file that you want to download the sequence for. Modeler then will query the PDB file and bring back down the primary sequence from the protein database. It'll produce what's called an alignment.ali file. Actually, that's a little bit of a lie. That's something that I modified. So let's see. What it will provide you with is this 4WEI.sequence file. So this is the primary sequence of the protein, okay, which it obtains again from a sequence database. And you'll see here that there is nothing missing in this sequence. So all these amino acids are filled in. If we look back at this file now, the alignment.ali file, okay, what I've done here is I have created a copy of that sequence, but I have put in explicitly where those missing amino acids are in my PDB file with these dashes. So then you have two copies of this. You have the dashes here, and then you have the copy with those amino acids filled in. So this is actually what those amino acids should be. You have a loop model script, which is included with Modeler, which then you tell it to basically create some models of what that loop region might look like and build those amino acids back in based on that alignment.ali file. Yeah, Rebecca.
Did you get to know which amino acids should belong in those empty spaces?
You have to do a little staring at the PDB file to figure out kind of which amino acid is right before the deleted region and which amino acid is right after, and then you look at the sequence file and you figure out where those are in the sequence, right? You know the numbers of the amino acids, so you can just count. So there's a little bit of counting, a little bit of just fishing around to line that up where it needs to be. It's not too hard once you know what you're looking for. But yeah, it's basically comparing the PDB file amino acids that you have, and then comparing that to the complete sequence of the protein from that seq 4WAI.seq file. Does that make sense? Kind of what's going on there? Or because remember the PDB file had one of the columns was the 3-letter amino acid codes of each of the amino acids, right? So you can figure out what those correspond to in the primary sequence. Okay, so anyway, so if you have this installed, you would use kind of this type of workflow to model things back in. There's also an online modeler server that you can use as well to do some simple loop modeling. I typically just use the Python package because it's quick, but there's also some ways to do this online. Okay, so let's go ahead and talk briefly then about the project. So if you look in these project notes, so after you go through your trip page stuff, make sure you can get this stuff to work. What you're going to do is you're going to download one of these 3 PDB files from the protein data bank. And I'm actually going to pair you guys up into groups of 2 to do this because, like I said, these have disulfide bonds in them. And so what I would envision happening, would like to try to see if we can observe, is that one person in each group of 2 will run the protein without adding the disulfide bonds between the cysteines, and the other person will run the simulation and have the disulfide bonds added appropriately within their structure. Compare those and see if we see differences. So, what are the things that can happen if you're not careful when you run a protein simulation? That's kind of what I want to see if we can figure out. So we'll just go ahead and pair up. So I'll just do 1, 2, 3, 1, 2, 3. So what's that? So 1, 2, and 3, and then 1 with Matthias, 2 Troy, 3 Rebecca. So pair up with your same number. And so the 1s will do the 5E5Q PDB. The 2s will do the 2NLS, and the 3s will do the 2QT4. And then try to set up basically a simulation following that same trip gauge protocol for this system, except you're going to have to figure out how to add disulfide bonds. So searching for that SS bond keyword in the protein databank file, and then trying to figure out within TLEAP how to add that. And I gave you a little bit of a hint here. The command should look something like this within the TLEAP file. And so you can go ahead and play with that and try to get that to work. Okay, any questions about any of this stuff today, Troy? Yeah.
Besides doing on VMD, is
Uh-huh.
there a way to check to make sure that disulfide bond is made?
So there are ways to check and see that you actually made the disulfide bond. So there's a an Amber Tools program. What is it called? AMB or
Yeah, and BMask, I tried that. And it didn't.
yeah. Actually, it may be PARMED. So they have one called PARMED. Either AMB Mask or PARMED. One of those, and I forget off the top of my head, but we can look at it. You should be able to query bonds from that. And so basically these are command line tools within Amber where you can read in the parameter file and say, do I have a bond between these atoms? And if the bond is there, it'll go find it and report it back to you. So you can double check that you've actually made those bonds in the system. Another way you could do it is, since you're working with somebody else on this, one of you makes the parameter file that doesn't have the disulfide bonds. One of you makes the ones that does. You put those both on in the same directory or somewhere, and then use the diff command on them. I'm not sure if any of you have seen the Unix diff command yet, but you can do diff diff file 1, file 2, and it'll go through and it'll compare the files and show you the differences between them. So you should be able to pick out if there are actually differences between the two files and see that those correspond to the disulfide bonds as well. But the easiest way is probably to use AMB Mask or PARMED, whichever one actually works. I forget which is which.
And then the other question is, if the PB files have like multiple slides or multiple frames to them, so always use the first one, I'm assuming?
Yeah, so if the PDB files have multiple frames, for now, let's just use the first one. If they have multiple chains, so we didn't actually talk about this, but sometimes you have multiple subunits that are within a PDB file. Just use the first chain, which is typically called chain A. And so when you save in VMD, you may have to make a selection, which is like protein and chain A or something like that, in order to save just a piece of the system that you want. You can use VMD to do it. You can also just use the text editor to do it, right? You can go into text editor and you can just cut and paste the lines that you want from your PDB file into another file. So I mean, there's again a bunch of ways to do this. VMD is just one of them. Yeah, Ellery. Okay. Other questions? Okay, so yeah, so give this stuff a go. So comment your input files. So use the Amber manual to figure out what each line is doing. I have a lot of comments in some of them. I forget when I added those comments. Some of them may be wrong. So take a look and make sure you understand what they're doing. Run through the rest of the trip cage stuff, and then go ahead and get started on these systems. Troy, one more question?
Should we run it exactly as we ran the trip cage, like same input files?
Yeah, you can follow that protocol. I mean, you'll have to change some things, right? Like the restraint mask, these are different proteins. So they're different lengths. So if you use the same restraint mask, right, then you're going to be in trouble because trip cage only has 20 amino acids, but these proteins have however many amino acids they have. So things like that you'll need to be careful with. But start by just running from the same set of input files. If things don't end up working okay, something crashes at some point, then maybe you have to think a little bit harder about why that's occurring and modify your input files a little bit to get around it. But you should be able to follow the trip cage protocol more or less. I have not tested the trip cage protocol on these three systems, so I have no idea what we're actually going to find with these three systems. We'll figure it out and see what it looks like tomorrow. Okay, good. So if there's no other questions, then we'll go ahead and wrap up for now. And I'll be around, like I said, the rest of the day. As you know, I'm in the office right next to Martin. So feel free to stop by if you have some questions.